morning and welcome to Race Industry Now, the weekly webinar series from EPARTRADE, presented to you by ARP, Performance Plus Global Logistics, PIC, ShopMonkey, and Fifth Third Bank Motorsports. I am Francisque Savignan, the founder and CEO of EPARTRADE, the global platform for the performance and racing industry. This is episode 352, and we're going to be talking materials with Materion. With me this morning are Judy King, the co-founder of EPARTRADE, and our superstar host, Mr. Jeff Hammond. Judy.
Thank you, Francis. Today's going to be an exciting webinar. It's hard to believe that we've produced 350 of these now, but we are just over 70 days from airing Race Industry Week, which is our 4th annual. We're confirming all those industry leaders right now. So it's going to be another great year. If you haven't signed up, please sign up so you don't miss out. And it airs November 27th through December 1st. So be sure to sign in for that. Jeff?
I think I'll sign up.
We need
Did I give you a heart failure for a second?
I think you did.
Yes, we lost you too. So yes, we're glad you're back.
Well, I am too, because all of a sudden my screen it froze, and it's like, now what would Reed do right now? Oh, reboot. That's what I was doing. Hey, good morning, Dave. How you doing?
Other than being on mute, I'm okay. Good to see everybody. Good morning.
Well, it's good to see you and good to have you on here. We were just laughing about the kind of consequences of whatever had happened a moment ago. I thought for a second I was lost out in cybersphere or something like that. And I was getting ready to say, well, Dave's going to be on his own if I can't get back on here. So I'm sure you can handle it. So are you ready to go today? We really want to learn some more about what's going on at Materion.
Sure. Yeah, I'm glad to be here. Thanks for thanks for having me. I think we did this just about a year ago, if I'm not mistaken.
No, you're right.
On some engine testing, and it's a great venue, and I'm happy to be working with you and the EPARTRADE team.
Well, I'm glad to be able to kind of continue because it keeps me caught up with what's going on in your world, and to me, your company is so fascinating, and the areas that you're looking into. I guess we pull a little bit of Star Trek or something out and say, you guys are boldly going where no man has gone before, and you're experimenting on stuff that, if it works, it's going to have a huge impact on our world. I mean, it's not going to be just the United States or in a certain industry. It's going to have an impact, I think, across the entire globe as far as that's concerned. And again, with the success you've had in the last 40 years, with everything else you guys have touched and done, it's got to be exciting.
Oh, it sure is. It really is. And this is a lot of fun. Racing is the R&D for the cars we drive, among other things. It's a lot of fun too. But that's where we learn about the next generation and what goes into what's going to be on the street. And that's kind of what we're going for here. Thinking about alternative fuels and those kind of things.
Well, and I got to ask this question, I think, leading off, because some people are out there scratching your head saying, why alternative fuels when everybody knows that everybody's trying to go with electric? And I think they fail to realize we're still going to need to have alternative fuels. I mean, we're not just going to go and like switch of a light switch, throw the light switch, and we're going to be electric. It doesn't work that way. And there's too many things that are going to still need to be addressed and move forward. And probably some of the byproducts and stuff you're going to learn from working with alternative fuels are going to help you even in the electric industry. Am I wrong?
Oh, yeah, definitely. I mean, and what we're going to talk about today, hydrogen is a fuel. I mean, we're also working with hydrogen production, and the hydrogen effects on materials is something that we study all the time because it happens in corrosion. It happens in a lot of the underground work we do, or our materials do.
I can attest to that. I had some material failure this past week. I got a little cabin up in the mountains of Boone, and I went in there to, all of a sudden it had no water. And we started checking, and we had situation where the power line that was buried underground had corroded and failed. So I guess I think I'm understanding what you're saying.
Well, yeah, and when you look at the alternative fuel thing, I mean, batteries are fantastic. I mean, battery electric vehicles, and they're coming, but you need an alternative. You need a suite of things. We can't just use one technology, especially when you start thinking about storing the energy, right? I mean, how do you, just from a power gen standpoint, how do you charge a car when the grid goes down after the hurricane? If you have a hydrogen internal combustion engine generator that can run, you might be able to charge your electric battery or put hydrogen in your car and make it go someplace. So these are the kind of alternatives that we need. And for long haul transportation and other things, I'll touch on some of that during this. So yeah, I think it's going that way. And because racing is, as I said, it's OEM R&D, the OEMs that are interested in hydrogen combustion engines are the ones that are pushing to have hydrogen series in racing. And we see that coming soon. I mean, Le Mans says they're going to have a all hydrogen series in 2030, for example.
Well, I think, again, you keep talking about it, but there's a perfect example of one of the ultimate tests that you will run into. And if you can survive something like the 24 hours of Le Mans, you probably got a pretty good piece, because they have just put everything under the max load for a long extended period of time. And the data that would be gathered off a vehicle that has completed that is going to be, invaluable, and at the same time, so much more informative than what you run through a computer even. So it's actually happened. I mean, that's the cool thing about it. It will actually you're not going to sit here and say, okay, we run it on dyno, we run the simulations and everything looked good there. No, we ran it in conditions that you can't simulate in a simulator. I don't care who you are. On track stuff is the best way to be able to feel 100% sure that what you were saying is right.
Sure, exactly. And we studied how our materials, how hydrogen affects our materials for a number of different reasons. One of them is use in propulsion, right? And then we started talking to OEM race engine builders and builders for the OEM teams, and said, "Are you guys interested at all in hydrogen? I mean, you're doing stuff with mostly fossil fuels right now." And they said, "Yes, very much," because the design engineers at the OEM level keep contacting them and saying, "Hey, what should we use here? What should we use there?" Including with hydrogen, where their experience so far is limited. So hopefully this gives them a little bit of a head start and a couple of tools to keep in the mental toolkit in case you see something that doesn't look right in the future.
Well, what I love about it is, you guys are collaborating, and they admit we don't know what we need to know about what you already are working on. So that puts them about 2 jumps ahead of everybody else. Because if you're trying to start up something, first you got to identify people that can come in, then you got to put in a facility to try to do it and hire more staff. So here comes you, Materion, who's, like I said, got a track record of making stuff like this happen. I can't see a better way for anybody to move off into this uncharted territory than with you.
Oh, well, thank you very much. I hope the rest of the audience sees things that way, but at least I hope everybody can go away with something they can use today.
Yeah. So what have you got for us? Because I got my pen right here, and I want to learn something, and I want to ask some questions along the way, because I'm truly I get fascinated by the stuff that is coming out of your company, because again, it's so cutting edge.
Okay, so as I said, some of this work we've done just to see how with all the hydrogen development, how our materials work in hydrogen environments. And especially do they get brittle, because hydrogen can make some metals very brittle and cause some failures. And we've put that together with some of the engine testing we've done, and haven't tested it and tested these materials in a hydrogen ICE, but we have materials that have been proven in ICEs, proven to have benefits, proven to have the durability, and also show that they're sort of immune to hydrogen. They do just fine, where other materials may not do so well in a hydrogen atmosphere. And it's early in the development of hydrogen ICEs. I mean, they have some that have run, and you know, some have run in races recently. Some have been on highways, but you don't know what the effects are going to be long term, because these are all prototype engines. So there may be some things that happen in the long run with the materials, and hydrogen effects on materials take effect over time. It's a slow embrittling effect.
Okay, so I'm going to go ahead and jump in here right now and ask that one of those first questions that in reading your questions that made me wonder. You know, you guys have been so successful in the aerospace in industry with your materials and everything, and the way it has held up, you know, on airplanes and things. So when you're talking about long-term effects and breakdowns, what kind of time frame do you, when you're building this in, I mean, how do you start looking at it? Do you look, I know you would look at it, you know, if you did it immediately, you know, a year, but for you to feel confident as you move forward, where does that comfort zone finally hit in? Is it even measurable? I mean, or is it just continue to move the scale?
It's a good question. I think what the industry or metallurgy tends to do is, some of the testing we're going to show you is accelerated testing. So it is drive as much hydrogen into the material as it will absorb, and then see what happens in a accelerated environment, put it that way.
Okay.
So okay, so I think be about time to start talking about what we have here, and if that's okay with you.
It's okay with me, but like I said, we've already got one question out there in the queue, and I'm going to save it because it has to do about specifics and testing. And since, you know, you're getting ready to start your program, let's go through your program, because you may answer some of these questions along the way.
Okay, and trying to get this, make sure I get this in and do, you know, justice to everything. I'll move fast, and please stop me if I'm going too fast. So
Okay.
this, let me see if I can. How do I share screen? Share screen.
Just do me a favor. Don't ask me to help you.
No.
There you go. There you
And
go.
what do we got? How about that? Can we see the whole thing?
It looks great to me.
All right, fantastic. Hopefully all that stuff on, oh, it doesn't even come in. All right, great. So I think, you know, you've gotten through my introduction by asking some nice questions. So I'll just move on to what we're going to talk about. Just a very quick glance at the company, who we are for people who don't know us, and what the racing and automotive applications that we have are. And then we're going to talk about, you know, hydrogen ICEs, a little bit about, you know, what good are they? What challenges do they pose? And then our combustion chamber materials and what they've done in durability testing in a gas engine. So we haven't tested them yet in hydrogen engines, but then go towards hydrogen embrittlement testing of those same materials and see how they work relative to other materials. So just a very high level glance at Materion. We have 3 business units: electronic materials, which is very semiconductor and electronics based; performance materials, that's my group and or my business unit; and a precision optics unit. Our founder was working on metallurgy in the 1920s, Charles Brush II, who founded the company and actually discovered the element, or isolated the element beryllium. That 1.7 billion is, we're on a high growth rate because it was less than $1 billion not so long ago. And that 3,700 employees, I remember a 2,200 number not very long ago. So it's a dynamic growing company, and you touch our products every day, or they touch you somehow, whether you know it or not. Talk about where we are in automotive industry and in racing. The one at 12 o'clock, the mission critical connection systems there. Those are high reliability electronic connectors. So those are copper, beryllium, and other copper alloys that you put in places where there's heat, where there's vibration, or it's a safety system where you don't want the electrical connection to either let go, relax and let go, or vibrate away. And you need to conduct the heat and electricity effectively. That is the largest participation in the automotive industry. And of course, it bleeds over into racing. The efficient combustion, those are the parts we're going to be talking about here. Those are the ones that you know from racing. I won't go through all of them. You'll see them. And the other ones, as we're following the industry, just like we are here now with hydrogen, we're following the industry into the EV realm, where we have some dissimilar metal connections that do nice interconnects, some e-axle bearings, which are the same thing as the engine bearings, and thermal management substrates. So we are automotive industry is a focus for us, and by relationship, as I say, is racing is the R&D, racing's a focus. 150 years ago, Jules Verne wrote in The Mysterious Island that we're going to use electrolysis to make hydrogen for energy. So it's been around for an awfully long time. And as you say, we're going towards electric vehicles. Now, hydrogen is a necessary, because it's a green energy. If it's produced greenly, it's a necessary component of future energy for us. Hydrogen ICEs, what's good about them? Well, tank to wheel, there's zero CO2 emissions because the output is water for the most part. And if you can use green hydrogen, so you're not making it using coal, you're making it using wind power or solar or something green, you've got well to wheel green or zero emissions, right? And that means you're not also putting holes in the earth, another environmentally friendly thing. The other thing that's nice about the hydrogen from an internal combustion engine point of view is we're almost ready to go. I mean, we have factories, we have technology already there around the fossil fuel engines. Putting hydrogen in them causes, you have to do a few tweaks, but it's ready to go. Whereas something like fuel cell, where I'm saying the technology bridge, is going to take longer to ramp up. And as a technology bridge to fuel cells, you'll have things like those hydrogen fueling stations and safe tanks to put them in, and a whole hydrogen delivery infrastructure that could come along with the hydrogen ICE that'll be ready for when fuel cells are ready to be put where they work best. Another benefit versus an electric vehicle is it refuels just like gasoline or diesel. It's very quick refueling. And from a racing perspective, it mixes with air very easily and gives a fast combustion rate. So you got a very responsive engine, and it sounds like we're used to for racing. It roars. So
it roars or it purrs, one of the two.
One of the two, yes.
Yep.
Yeah. So and there's been a lot of investment in this recently. I mean, so the first three of them are heavy duty engines, but Cummins just spent over 450 million to upgrade their Jamestown plant to have fuel agnostic engines, which means they can burn gasoline or they can burn a fossil fuel, they can burn natural gas, another fossil fuel, of course, and hydrogen. JCB has just put $100 million project together for super efficient hydrogen ICEs, and next year, Deutz is going to start offering stationary power gen ICEs, and they're using Mala, a name that we all know, for the piston, pin, and ring pack. And then, as I said, this comes over to racing as the OEMs get interested in it. Toyota Gazoo just unveiled this year at Le Mans their Corolla concept vehicle, hydrogen ICE, and they're going to race it in 2026. And as I said before, Le Mans is going to have a class in 2030. An ABL Race Tech, just using water injection, has made a 2-liter 400 horsepower engine specifically for racing. And as the president of Yamaha Motors says, it allows us to be carbon neutral while maintaining our passion for the internal combustion engine. Right. So it's on its way, but there are some challenges. All right, and these are challenges that we can overcome. high production costs right now. In Norway, they've worked on it and they've got it down so that it's at a par with natural gas. That's Norway natural gas, not US natural gas. So it's still a relatively high price, but that's something that's being worked on. Energy, it isn't as efficient as electric motors, but you can get close to it. There is work now being done to get it close to fuel cell electric motor efficiency or electric vehicle efficiency. Safe and effective storage and handling. People are worried about hydrogen, but we did the same thing with fossil fuels that are explosive and poisonous and will asphyxiate you. And we can handle those just fine. We don't think about them as a danger. Or, I mean, we know how to handle them safely. Let's put it that way. They are dangerous, but we know how to handle them safely. Same will happen with hydrogen. The other thing that happens, as I mentioned, the efficient combustion, it's a high combustion temperature. So there is some NOx emissions that need to be controlled in the engine design as much as possible. And there's also thermal management issues. You're getting more heat. You got to have a way to either remove it or put it where you want it, keep it where you want it. So materials that can conduct very well and operate at high temperatures are important. Running a rich mixture in hydrogen isn't like running a rich mixture in a gas engine. It doesn't lubricate. And so you need a low friction materials that work well in starved lubrication conditions. And then, as I mentioned before, there are harmful interactions with metals. One is the embrittlement that we're going to talk about. Another one is corrosion. And as examples of corrosion, there have been reports or studies showing that hydrogen can remove the protective oxide on a stainless steel and cause it to corrode, for example. So that's not something we're looking at here, but something that we do need to be aware of. And those last 3 bullet points remind me of the mom who was watching the teenager go out the door at 9 o'clock at night and says, make good choices. Well, that's somewhere where the material choices you make can help. And you need to find materials that can work in low lubrication conditions, as I said, high temperatures, and then aren't bothered by the fact that there's some hydrogen around. So the materials we're going to look at today are our Supremex metal matrix composite. That is an aluminum alloy reinforced with 25% silicon carbide. It's been used in Formula One pistons before they banned it, and it's actually currently in the Gordon Murray T50, which we'll talk about later. Compared to aluminum alloys, it's the same density, almost within 2% of the density, but it's 50% stiffer and has much better fatigue strength. It makes a fantastic 2-stroke piston, by the way, with a lot longer life than the normal hypereutectics. And versus steel, the parts can be made nearly the same size, a little bit larger volume, but with the same stiffness at a much lighter weight. Same stiffness, the same strength. Our Performat alloy is it's a copper alloy, kind of call it alloy soup, copper, nickel, silicon, chromium, zirconium. It's used in valve seats and valve guides in a lot of racing classes. It's more popular in North America than it is in Asia or Europe. But compared to most other bronzes, other than the copper beryllium below it, it's a lot stronger, it's a lot harder, and even more so than the copper beryllium, it holds its strength at a high temperature. It also has very good thermal conductivity, so it can move the heat away from, for example, the valve head, or distribute it, or the valve head, or distribute it around away from the hot spots in the head. And then alloy 25, that's the oldest, well, I think one of the oldest materials we put into racing. I have found a record of us selling in 1984, selling some alloy 25 to a valve seat manufacturer who still advertises it by the trade name at this point. And that is used in aircraft landing gear, for example, it's main landing gear bearings. So from a bushing standpoint, it's great for that. It's also submarine hatch seals. It's very high reliability sealing. I'll talk about now. The other 2 materials, the Supremex and the Performat, we have engine testing recently. It's what was in the last webinar that I gave. We'll go over just a little bit of that today. Right. The alloy 25, I'm just going to give some examples because it's been around for so long that people know it so well. It's also called copper beryllium 2. It's 1.8 to 2% copper beryllium. So I'm giving just some examples of those. It is the original copper alloy intake valve seat at the high end of racing, and it's still widely used. There are some places that will not convert to anything else like a Performat alloy. And it does small end bearings very well too. From a small end bearing standpoint, if you see a very expensive connecting rod and it's got a copper alloy bearing in it, likely it's that alloy 25 copper 2% beryllium. And you can see that at the KTMS Motocross Action Mag said that it not only reduced friction and improved the durability over a needle roller bearing, and we've heard from passenger car designers, when you can switch from the needle roller to a sleeve, a plain sleeve, if you could do that effectively, you get rid of a lot of noise, vibration, and harshness in the engine. So that's all we're going to say. Well, other than that, sorry, I forgot I had this here. The one extreme example of alloy 25 is Jay Upton's 8,000 horsepower top fuel bike. And Jay actually makes the whole top of the combustion chamber. He gave me these photos. He makes the whole top of the combustion chamber out of alloy 25. Doesn't even need valve seats because it acts as the seats itself for the thermal conductivity and the high strength of the material. So moving on to the other two materials, right? In the last webinar, in last September, we talked about some engine testing that we did with Cosworth in the UK. There was a 2.3 liter EcoBoost crate engine that we took and had them redesign specifically the piston, the pin, and the rod to minimize the amount of mass. As you can see in the green box, they took out 30% of the mass, 1.4 kilograms, by reducing the piston weight by 20%, just making it thinner in places where the aluminum had to be more bulky. And by replacing a steel rod with an aluminum rod, they took 40% of the rod mass out of it. And at the same time, installed Performat seats and guides. The engine mapping and all of that is in a white paper that we have. It's in the other, I won't go through it today. It's in the other webinar. Theoretically, we should have seen a 5% reduction because of the mass reduction, should have seen a 5% reduction in fuel consumption. We didn't because the engine wasn't designed around it, so it was running naturally unbalanced. But going on to the durability test, this is going to show that these materials are set to last. Is we put a fresh set of those parts in, or they put a fresh set in, and did a 150-hour wear test. And that's 15 minutes at idle, followed by about 17 minutes, or is that 13 minutes? Sorry, 13 minutes at max torque, about 10 minutes at max power, and a couple more minutes at 90%. Rinse and repeat, 225 times. So that gives you 96 hours at wide open throttle. And the data I've got, if you want to see it, if anyone wants to see it, I've got my email address at the end of this. Send me an email. I've got 300 some slides of data from Cosworth on this. But all the data was stable, aside from the fact that they blew the head gasket twice, which meant they were running the engine really hard. So let's look at very quickly what happens. The engine strip, the valve seats were in perfect condition. The recession was 1 to 2 microns, unmeasurable. The guides looked brand new, as far as I could tell, and the valves themselves had no measurable wear. This meant the seats were providing some nice resilient cushioning onto the onto the surface of the valve head. For the pistons look great. The pistons really did what they were expected to do. Cosworth engineers knew that they'd seen these things run in Formula One, so they expected this to happen. There were a couple of issues in the lower left of the top groove flatness and a little wear in the rings. Cosworth themselves have overcome that, and we have figured out how to do it ourselves, so we could tell you how to do that. But they were so enamored with the pistons that they decided to put them in the Gordon Murray T50. And that's the standard for that 12-cylinder, 12,000 RPM, 660 some horsepower engine. For those there's a vlog on YouTube with Dario Franchitti talking to Gordon Murray about the design all the way through him getting onto the track with it. and testing it. But episode number 9, where they get it up to 12,000 RPM in the dyno, is spectacular to see. I recommend that to people to watch. And there's that roar, or more of a whine, but a beautiful whine, that we were talking about not wanting to lose. And with the connecting rods, okay, these aren't going to be in the these aren't going to be directly in the hydrogen and a hydrogen ICE. They'll be in the bottom end. But the fact that you can take a connecting rod, an aluminum material, and substitute it for steel is notable here. And the Cosworth engineers had not seen a connecting rod in this material run before. They were impressed. There was a little bit of fretting on the back end of the bearing because thermal expansion is different from steel, so it lost a little bit of the interference fit. That can be a good bearing choice, a better bearing selection or matching will help with that. And the tough met bearing material that's in there worked just fine. And we've had a number of connecting rod manufacturers tell us that tough met and copper beryllium, you can't tell the difference between the two. So we assume the copper beryllium would have done the same thing there. But are these materials candidates for ICEs, right? They're all proven to work in racing and durability for on-highway engines. They have meaningful benefits, right? They work in the tough conditions of high heat and low lube, but how do they do in hydrogen? And do they do things like crack like that, or get embrittled? And so far, there haven't been many, like I said at the beginning, there haven't been many problems to date, but there hasn't been a lot of work done, a lot of time in the engine so far. But what happens, and I won't go into the mechanisms of hydrogen embrittlement because there are so many different mechanisms, but essentially hydrogen gets inside the metal, finds its way, either is in when it's made, I'll talk about that, or finds its way in, and then goes to defects. And if those defects slowly, and makes things brittle at the defect. And as those defects stretch and get bigger, the hydrogen rushes to it. I'm being very simplistic, but the hydrogen rushes to it and makes it more brittle. So that's why over time, this sort of thing happens. The sources to get hydrogen into a material, it can happen in the fabrication of the material. That's all the stuff from 3 to 9 o'clock there. So in the making of steel, in the casting, hydrogen can be driven in. Welding can do it. Heat treatment, of course, pickling, and even electroplating, right, can have hydrogen moving into the material and causing it to be brittle or get more brittle as time goes on. The other ways you can get it is, think of a hydrogen tank. You've got pressurized hydrogen that can force hydrogen into materials, and then corrosion also, rusting of metals can do that, for example.
All right, let's take a quick pause here. I got a couple we here, and I think we don't want to get too far out in front of this thing, because you just showed the piston and the parts that that were coated and condition of them. Number one, what type of wrist pin did you use, and was it coated or uncoated? Because you just brought up what you can do with the pickling and all other stuff to go with it.
That was a DLC coated pin.
Okay.
And it, yeah, definitely a DLC coated pin. We've seen it run. We've seen those materials run on hardened steel and chrome plated pins as well.
Well, Brent Johnson was the guy. He asked that first question. He said about getting into some of the specific testing. Is there a protocol or a routine that you guys go through with a lot of this stuff that kind of compares other previous tests that were run? Just, it looks like you come a long way in a year since we originally tested, and you showed the stuff that you were doing then. So throughout this process, once again, specific tests, at what? I mean, exactly how do y'all, I know you got to have protocol for what you're getting ready to do so it repeats, right? And you got something to look back at.
Right. Well, I mean, the idea behind this is, but the testing we do is to give people a level of comfort. It's just, this stuff, it may not do exactly what you want in your engine, and you may have to make some design tweaks to get what you want with the material, but the comfort is, it's expensive to put something on a dyno. and if we do it once, at least you've got the idea that those materials will hold up. We've talked to some researchers who every time they want to run an engine hard and they want nothing to go wrong with the piston, they make the piston out of Supremex, whether or not they're going to have a Supremex piston, in the final the final iteration of it. So these, this is more not to give you a on-off switch like you can use it exactly here, but it's more to give you a comfort level. Every time you put something in an engine, you have to test it, and we hear that all the time. I mean, we've got people with the valve seat material. We offer 3 or 4 different materials for valve seats, 4 different materials for valve seats, and we have some years somebody buys a bunch of one and then they switch and buy a bunch of another. And I said, what's going on? I said, well, every time we tweak the engine, a different material might run better. We may not need this one, we may need that one. And so those are the kind of things where you gotta try it yourself. But we're hoping that this gives people more of a level of comfort to try.
Yeah, very good.
Question.
Mm-hmm.
All right. So from there, I'm going to give just a couple examples of the kind of things that can happen. And it's, as you'll see, this isn't catastrophic failure immediately. It's a failure over time. The University of Bochum kindly gave us these. I don't know a lot of the history about them, but in offshore wind turbines, these nuts and the nacelle, just after a fretting sort of fatigue situation, they cracked after a while from corrosion. The drive shaft in a car, same thing, cracked. And talk about a slow, long time crack that did some really bad damage. That bridge in Mexico that fell. It was they definitely chose the wrong steel for that one in a corrosive environment. So it can be because catastrophic. The failures could be catastrophic. They usually are. And what happens is if it's over time, as I say, as you pull the metal, you create some more defects. The hydrogen tends to rush to those defect areas and make them more brittle, which then slowly accelerates the and makes the cracks grow right where they are. So just to go into the materials again very quickly, why we're looking at these materials and related to hydrogen. They're all copper and aluminum based. They're face-centered cubic. And the reason I talk about that is that's the lattice structure. Body-centered cubic, which is a steel structure, tends to absorb more hydrogen or absorb hydrogen more quickly than a face-centered cubic. They all have higher strength values than traditional alloys, and these are right out of production. And we haven't done anything to the service. This is, if you called us and wanted to put something to test, you bought material from us or one of our distributors, that's exactly, this is exactly what you would get. I won't go too much into the graph of the properties, but talking about getting a little more materials techie here, for as much as I am able to do that. The alloys or the materials, you've got the copper beryllium, which I mentioned is 2% beryllium with some addition of cobalt. It is the strongest in a bulk form and something that you could use for engine components like a rod or a tube to make valve seats. It's the strongest commercially available copper alloy. It has, and then the Performat with a lot more thermal conductivity is still quite a bit stronger than your average copper alloy. And Supremex can't compare to those two, but it is, as I mentioned, 50% stronger than a standard aluminum alloy because of the silicon carbide that goes into it. And then looking at the matrix, the different matrices, so the copper beryllium, the reason it gets so strong is not only does it have hard particles in a soft matrix, which is a strengthening mechanism for all 3 of these materials, but the copper barylides are coherent with the matrix or the lattice of the copper. And so what it does, but they're tighter together. So when they form, they pull the copper matrix together. And so now you have it pulled together, and that's an extra amount of stress or strength you have to overcome. When you stretch the material, you have to overcome that plus what's already in the material. So that's why it's that strong. But in doing so, you've got that distribution of all those barylides that kind of mucks up the matrix, and it doesn't conduct heat or electricity, but mainly heat for our purposes, as well as the Performat alloy. Performat has very hard nickel silicides in a copper alloy matrix, and those are, but you see there's conduction paths in between it. And the reason going to the Supreme, that's Performat Supremex, again, those are 0.3 micron average size particles, making it easier to machine than, for example, cast MMCs. But that has a higher thermal conductivity than aluminum itself slightly, because silicon carbide conducts heat better than aluminum. Now, when we asked my colleague, I got it. I skipped one. Come on. There we go. When I asked my colleague, Dr. Andreas Freyne, our Director of Technology and Innovation in Europe, to find the best places to test this stuff, he found two really good ones in Germany. Ruhr-Universität Bochum and Decima are top class places. I won't go into the details, but at each one, we did some testing. And the first thing was what they call hydrogen loading, right? And at Bochum, it was gaseous. So a high temperature, 300 degrees C, 20 days of just pressurizing and pushing the gas into the samples. And when they were done, they pulled them out, and before any other testing, put them in liquid nitrogen, because that kind of holds the hydrogen in place. It doesn't allow it to move if it's that cold. And for a higher concentration of hydrogen at the surface, you use the electrochemical loading, and that's a sodium hydroxide and arsenic bath that it's in, which puts more H2 at the surface, as it says, and you would expect more loading, more hydrogen passing into the samples at that point. So the techniques that we used, again, there's we can give you details on this, but mainly what we're going to be talking about is the thermal desorption mass spectroscopy, TDMS, and that will give the total hydrogen content in the materials. There's also a permeation cell. We don't talk about that in this, or I don't talk about that much in this presentation, but that shows how the hydrogen moves through the samples. And getting to the heart of the matter here is that in the delivered condition, all three of these alloys at TDMS didn't show any hydrogen. You couldn't find it. So hydrogen is not, we're not putting hydrogen into them in the fabrication of them. With the gas loading, those are still very small numbers. They're not absorbing a lot of hydrogen. That's 0.02 parts per million. So put 6 zeros on the other end of that thing. And the Supremex was below the detection limit. We have not yet used the Supremex in the electrochemical loading in the liquid bath, but as you'd expect, it's slightly higher, but still below 1 part per million. So it's not much hydrogen getting into these samples. And then the next thing we looked at was slow strain rate testing. As I mentioned, the slow strain rate, it's not a normal tensile test. You can see the tensile bar there just to the right in between the two photos. It's not pulling that at speed like you do in a production facility. It's a slow tensile test, which allows some defects to form and the hydrogen to move into those defects. And then the values we looked at were the relative elongation and the relative reduction in area. That means an elongation is how far that sample is going to stretch before it breaks. So it's the total plastic deformation, and the reduction in area is how narrow does it get effectively where it fails? How much does it neck down? And so loaded versus unloaded means at 100%, absolutely no effect. At 2%, it got really brittle, and anything above it, anything above 100, it got more ductile. And then we did fractography. I don't have that in there, but we have the images, and they're in a paper that we've written. So we'd be happy to share that with anyone who wants to look at the fracture surfaces of the materials. So the last important slide here is where all the meat of the matter is. So the top 3 rows on the top table is what I just showed you, and this is with the gaseous loading. I don't have the information for the tensile results on the aqueous or the liquid loading yet, the electrochemical loading. This is just for the gaseous. But you can see, first of all, with the austenitic stainless, a nickel-based alloy, and a ferritic stainless, all have some hydrogen in them to start with, and then all of them absorb some hydrogen along the way. The ferritic stainless less than the other 2. And then looking at the relative elongation and relative reduction in area, remember 100 is the 100 means no change. So Alloy 25 and Performet and Supremex all did relatively well. Those are numbers that people who worry about these things are not that worried about. And the nickel-based alloy is also in there as well. The thing about nickel is, nickel is good in high heat, and it's very strong and very hard, or nickel alloys. They're not great in friction. They don't conduct heat very well, and they're very heavy. So there are a limited number of places where you can use them. But you can see the stainless, which you would think would work better than a normal carbon steel, which would absorb less than a normal carbon steel, still has shown a lot of embrittlement. The elongation going down to 40% for the austenitic, and closing in on or more than a 25% loss for the ferritic stainless. So, and the upper right-hand corner is, I asked Andreas, my colleague there, I said, Dr. Frayne, what happens with titanium? And he said that you can't even, it crumbles. Titanium sucks up hydrogen and creates hydrides that he said when you do that to the tensile sample, it's not even able to be tested because it's just so corroded. So titanium isn't something that could be used there. You're trying to get to some questions here, leave a little bit of time. I'm just going to go to a quick review just to say that, hydrogen ICEs are going to be here. Racing is going to be part of the development. There are challenges. Embrittlement may be one of them to materials that are used with hydrogen. And now, as I said, the mental toolbox, you've got some materials that aren't going to be affected and also run or have benefits for running in an engine. So with that, I'm going to move on to overshot. There we go. Anyone is welcome to contact me directly. We also have a crack tech services group at Materion who has a database of every piece of data we've ever taken on our material going back to who knows when at their fingertips. And these are really smart people as well. So we'll be more than happy to take questions after the fact. And I think we've got a few minutes left for them right now, if there are some.
Well, thank you, Doug. And yeah, folks, I know you're out there, and I know everybody's been just like I have, watching and looking at numbers. So if you got any questions pertaining to that came out of this, please speak up. We got time, like I say, to discuss that. But from where you were a year ago to now, very impressive. And once again, the idea of the process and the protocol that you put in place seems like it's repeatable, and you can rely on what when you start crossing the two, what you did earlier and what you're doing now, I'm assuming has matched up quite nicely.
Yeah, it has, and that's actually what this is the marriage of two different different sets of testing. And we went to some of the best places to get things tested. And that's when it's always helpful when you can do it on the outside. Get somebody who's independent to put their name on it with you. That takes away our internal bias, which we try not to have, but you can't avoid it.
Well, so are you? I'm pretty sure you are, but what are you currently working on as far as just a continuation of what you shared today, and then, like I say, some of the open-ended stuff that you started, like testing, and is that where you guys are at right now as far as your process?
A lot of what we're working on now is reducing the cost.
Okay.
I mean, and it's a chicken or the egg. As you get more volume, you get lower cost. But if you don't get lower cost, you can't get more volume. But we are working at ways to, do what is done in mass production and to make these things more friendly for everyone. And reducing the cost may be figuring out, as we're doing, how to machine the SupremeX alloy more effectively. And we came up with a machining guide to do that. Or is it, how do you mass produce in near net shape a valve seat? Because the iron-based materials are made from powder directly into shape. We're giving people a tube, they got to machine it. How can we get closer to those kind of things to make it more friendly so more people can use it? And eventually that's the path into mass production of these materials. So we're reaching both ends. It's how do we make everyone able to use the materials? How do we get everyone able to use the materials, as well as what's next? And as well as this, we're working on the example I gave, materials for EV drivetrains.
Right.
And same sort of thing comes up when you have an 1100, 1200 horsepower EV. It puts some challenges on the differential and the gearbox. You
think? I know what it does at 750 horsepower, much less 1100. Golly, bum. Well, Dave, I mean, Francis is either laughing at me or laughing at you, so I'm gonna let her laugh at me. And the thing is, you guys continue just kind of like to, I'm impressed that you're taking something that the elements are so simplistic and doing so much with them. I think that's the thing. It really blows my mind. I mean, this is not something that, you're going to outer space to bring in here to try to create something. It's something that it was existing, and this somebody needed to figure out how it worked into your already project with Beryllium and everything else that you guys have created and continue to work in this industry.
That's the idea. The easiest way to solve a problem or take a technical step is switching the material. If you can just do that, you don't have to change the design. There's so much, you don't have to retrofit. You don't have to change your factory. You just put a different material in.
We've got a very quick question, Jeff, because we want to address that one very quickly, and then we'll wrap it up.
All right, we'll bring us back up here so that we do. Again, Brent Johnson, he'd like to say, thanks so much for the presentation. Curious, what makes SupremeX so expensive to make?
It is, without giving away how it's made, you saw that nice uniform distribution of the very fine silicon carbide particles. That's not easy to do. If you've seen, you can go online and find pictures of the microstructure of a cast, for example, MMC. There's big globs of silicon carbide in there. Those things are very, very difficult to machine, and the properties are not isotropic. They're not the same in every direction, because you got a clump of a hard particle, or a clump of hard material, and then some soft stuff over here. So what we call mechanical alloying, making that. After that, it's a lot of powder metal processing, but getting the right materials, getting the right size of the materials, and then making sure they're uniformly distributed is part of the reason. And as I said before, we are working on ways to reduce the cost of the materials, and SupremeX is one of them, because we know a lot of people would love to use it for pistons and rods. And
well, and I think you've done a really good job of pointing out and think about it like this: you got aluminum and you got cast aluminum. If you want good aluminum, you got to get pure aluminum. And I mean, that's what you're doing. You're getting a pure product, and to be able to have that pure product, it takes a lot more refinement and processes to get it to the pure point. Is that simplistic enough?
Yeah. And like I said, that's they're also aluminum powder, it's rocket fuel. So there's some other things that go along with it that make the handling. We do it well, but it's not easy.
Well, again, thank you very much, sir. It's a pleasure to get a chance to spend some more time with you. a year later and see where we've come from and where we're going. And Francis, I think we need to have him back here maybe in another year and see how much further we got.
Absolutely. Brilliant
All right.
presentation. Again, Dave, thank you very much, for preparing all that. So thank you very much for being with us today. This webinar has been recorded. It will be posted later on the EPARTRADE platform, distributed through our newsletter channels and social media channels. In the meantime, we pushed Materion's products back on the homepage of EPARTRADE. So please go to epartrade.com and take a look. We will be hosting CP Carrillo next week, and we will be talking pistons. Thank you very much for being with us today. Let's go racing. Bye-bye.
Okay, thanks.
EPARTRADE is a digital platform that we've created basically to make life easier in the business community of auto racing.
EPARTRADE, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier.
When you see a product that you're interested in, all you need to do is click on request more information, and then from there, it is forwarded directly to the buyer or to the supplier.
EPARTRADE really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
Land speed record holder George Poteet's Speed Demon rocketed 481 miles per hour at the Bonneville Salt Flats. You don't go that fast without ARP fasteners.
There is no way that we could go the speed that we've gone, the number of times we've gone, with a lesser quality bolt than ARP supplies to us. And we absolutely wouldn't be where we were today if it weren't for ARP.
When failure is not an option, it's ARP-bolts.com.
We're Performance Plus Global Logistics. Our team of dedicated performance industry and logistics experts get valuable cars and components to the track on time in top condition. We provide expedited logistics solutions for the performance industry using direct routes instead of deferred options, and communicate all necessary information to the appropriate resources to meet regulations and ensure a smooth transit and secure delivery, both domestically and internationally. And we exceed customer expectations by providing best-in-class service with an efficient and cost-effective system in place. Contact us today to book your next shipment.
You work as hard as your truck, and you have no time for downtime. That's why more truck owners trust Blue Def, America's #1 diesel exhaust fluid brand. Each batch is guaranteed pure, so you can avoid costly repairs caused by inferior DEF. Demand America's best for your truck. Blue Def and Blue Def Platinum. Put trust in your truck.
With ShopMonkey, we've been able to grow the shop by 20% in gross sales since implementing it in the shop. Everything that we were doing before has been sped up with ShopMonkey. All of our parts ordering, all of our approvals, all of our mechanics knowing what to do next. And I've had friends that are in the trade that own shops ask about ShopMonkey, and I highly recommend it just because of easy use. There's nothing like it with that kind of platform.
With roots in the Midwest that date back well before the Model T, Fifth Third Bank has a long history of serving the needs of automotive companies. While much has changed over the years, our passion for helping businesses put cars on the road and on the track has not. Today, we are more committed than ever as a member of SEMA, a founding member of PRI, and a sponsor of multiple race teams across several racing series.
For over a decade, Fifth Third Bank has been a staunch supporter of our industry and a great partner for many companies in the motorsports field.
Our business has been growing extremely fast, and really we could not be where we are today without Fifth Third. They provided amazing strategic advice, the capital we need to support our phases of growth.
They are true partners for me now, and what they do with their involvement in motorsports is untouched in this community.
Where can we take your business? Fifth Third Bank.